Good afternoon. Welcome to Introduction to ML.NET. My name is John Alexander. I'm a senior content developer on the docs.microsoft.com team. And I've been working on ML.NET documentation, code samples, things like that. And I'm also just kind of switched teams to the Azure ML/Cognitive Services docs team. So today we're going to talk a little bit about this new framework that allows you to infuse machine learning solutions inside of your applications. So come along, won't you? The jokes don't get any better, so might as well laugh now. So machine learning, or learning itself, or diagnostics. Do you notice anything wrong with that wrist or the bone right below it? There are some cracks in it, right? So the Blue Mountains of Australia are extremely formidable, especially when there's a rock in the trail. Can you kind of understand where I'm going with this? So Monday, I was out on a tour, and we were going on a small trail to an outlook. Not like mail, but looking out. And I looked down and thought, it's kind of, there are a lot of tree roots and things. And I looked back up and I took a step. And I went, boom. And I landed like this on this hand, full weight. Why am I talking about this with ML.NET? So I go in, and there's a pattern that I go to the hospital, they take a look, they feel, and they recognize the pattern of this nasty looking bruise that was kind of starting to swell a little bit. And so they sent me to X-ray. They wanted more data. Okay? And took a look at the X-ray, and data came back with a high probability of a break. A fairly high probability, wouldn't you say? And so if you're going to break, your arm, you want to kind of do it right. So it's a compound fracture, but it didn't go anywhere, so that's good. So they said, well, wow, since John, you were foolish enough, in your 20 years of travel, you've always bought travel health insurance until this trip, we're going to stabilize you, and you can get it taken care of when you get back to the States. But they used the information that they had and the model inside their head to be able to correctly identify what was going on in that image. In the same way, we can use the data that we have to answer the questions about our business. And in this case, the question was, very simply, is it broken? Got the data back, and we could do a high probability that it was. So I will warn you that because of that, I'm on some pretty good pain medication at the moment. So this could be very, and in some pain. So I apologize if it's not at my usual level of presenting, but I wanted to go ahead. I mean, I was even telling them at the hospital, man, I got to do this presentation. I'm here for the conference. I've come all this way. Just cut the arm off. It'll be fine. Okay. So anyway, though, we have to be able to answer questions. So how many of you would consider yourselves .NET developers of some form or fashion? Okay. Yeah. You might have built things for the cloud, might have built things for the web, for the desktop, maybe even a mobile app or something cool for the Xbox. Might even have done something with an Arduino or a Raspberry Pi. But up to now, unless we were going to get into either pre-built models or have a high amount of knowledge to use things like the the CNTK, the toolkit, okay? Before that, we didn't have a decent answer to be able to start using machine learning in our applications. But before we talk about what ML.NET really is, let's take a step back and talk about why machine learning is different from the way we've done traditional programming. It's kind of, if you think of it, like we're programming the unprogrammable. So if we look at this question, is this a face? Well, yeah, right? I mean, duh. And that's a universal, I think that's a universal sentiment. You can say duh wherever you go and you understand that. Is this a face? Sure. How do you build a function to answer that question? Maybe a lot of if statements? I don't know, right? So, So how do we build a function to do that? What about, based on a description, figuring out the price of a shirt? You might be able to use keywords, something like that. But how would that scale if you could do that? So one of the things we have is a tremendous amount of data sitting around. I guess I need to stay by the microphone, so I apologize. We have a tremendous amount of data sitting around that we can utilize to create a model that recognizes the pattern of a face or not a face, based on example after example after example after example after example. You get where that's going, right? So it really isn't about the code necessarily anymore. It's about how we handle that data and what we do with that. So there are many machine learning many things that machine learning can answer for us. And we can kind of classify those down, and we're going to focus today on 3 of those. First off, how do we classify something? Is it binary? Is it A or B? Is it multi-class? How do we classify something? Sentiment analysis. Is this a positive or negative in my Twitter feed? You know, die you scum might be considered negative. Great job, positive. But there are things in between. So how much, how many? How much is that shirt? Can we predict that price? What's the weather going to be on Tuesday? That's a regression problem where we're trying to figure out, based on the series that we have, what comes next in that series. And then another one is, we've got a bunch of stuff that we need to organize. How can we do that? Like maybe topics for news items in a news feed. And that's what we'd call clustering. So you may have already started playing around with machine learning with cognitive services. I think there's about 90 different services right now that you can utilize and use different models already to be able to handle things, object classification and vision, pulling out speech recognition, translation, all sorts of different things. You could even do sentiment analysis using that as well with text analytics. So if we look at this, we're sending in sentiment. What do you think, guys and ladies? Positive or negative? Positive? Great vacuum cleaner. So we send that in, and it comes back 96% positive. Okay, sure. That's great. We can use that all day long. So we're going along, and it works well. And then all of a sudden, we get this. It's a positive or negative? You and I know, based on context, that it's probably positive, right? Based on a pre-trained model, though, it sees sucks. It doesn't recognize the context of that's what a vacuum cleaner does, right? It sucks a lot of dirt, like a Dyson or something like that. So we get that back, and that's 9% positive. So what do we do about that? Well, pre-built models can take us a long way. They can help us to build several different types of applications. But at a certain point, we may need to use and train our own models or get a model and import that in from our group of data scientists or somewhere else and be able to use that with our data. So that's where we come into ML.NET. So thinking about building your own models, and the first thing we need to do, once again, is come up with the question that we're trying to solve. What is that question? You guys seen the matrix? It's the question that haunts us, right? What is the matrix? What question are you trying, what can you answer based on the data that you have? So we can prepare that data, we can make sure it's clean, we can do what's called featurizing that and pulling in different, combining different columns, all sorts of things, so that we can better answer that question. Once we do that, we pull in the data, then we can build and train that model. But if you notice there, with those arrows, that's an iterative process. We look at that model, we train it, we look at the metrics, go back and we tweak it again, train it some more, and so on and so forth. Until finally, the metrics say that we have a good enough model, and we go ahead and deploy that to production, put that into a web API, utilize it in an application of some sort, mobile, whatever, and we go from there. So today, we're going to talk about solving 3 different problems with ML.NET. We're going to talk about issue classification in GitHub. And the problem is around what technical area does this particular issue belong to? Is it security? Is it I/O? Is it HTTP client? What might that be? So we need to figure out how to label that with issue classification. Recommendation. You might need to build into an application a service to recommend something. And we'll take a look at how we might build that with ML.NET. And finally, we'll take a look at, in this release, with the image classification capabilities that we have in the 0.5 release. And we're going to try to determine whether or not this is a dog. Okay? So what is ML.NET? ML.NET is a framework that's made for .NET developers. It allows you to build your own model, and it allows you to focus on things such as, like we talked about, sentiment analysis, predictive analysis, all sorts of different things that you might want to do there. It's proven and extensible. And you say, well, John, it just came out. How can it be proven and extensible? Okay, I'll take your cynicism. That's a fair question. It's been used by Microsoft internally for about 10 years. And if you've used recently anything in Office, like for example, the PowerPoint design ideas, if you've used that, or chart ideas in Excel, it's based on the ML.NET engine on the back, in the back end. It's also open source. It is open, and it's cross-platform. You can run it in Windows, run it in Mac, or Linux. Come on. So this is the machine learning repo. And there are several different things here. One of which is, you can see all the source code as it's being built. And We're currently on the 0.5 release right now, on our way to 1.0. There are some different internal docs in here. There are also some samples and some tests. We'll take a look at that in just a moment. So we'll get in more to that in just a few minutes. So, like I said, ML.NET is a framework, and it allows you to go from something with cognitive services where you might be using pre-built services into building your own model. And it's built based on a code-first approach so that you can utilize many different aspects of the API. Finally, one of the things that's kind of unique to ML.NET is the fact that you can save the model asynchronously into a zip file and then pull it back into another application. So, okay, we've got Python, we've got R. Anybody here use Python? Or here use R? Can you spell R? Okay. They're great. There's nothing wrong with them at all. I love Python. It's cool. But as a .NET developer, it's really challenging for me to be able to create a machine learning solution. So we want something that we can use natively. Okay. So currently, we have our APIs split out into two different areas, one for training and one for consumption. And so you need to be able, when you pull in data, to be able to transform that. So for example, on a text transform, you'd want to pull that in for data processing. You'd want to be able to change that around, do all sorts of things to break that text up in certain ways, pull out different words maybe, for example, all sorts of things you might need to do with text. You may need to also combine things or handle categories in a special way, and categorical transforms will allow you to do that. All sorts of different transforms. We have different learners that we can use, whether that be linear or something like k-means for clustering. And we have the MISC category. Every framework has that. So basically, when you're needing to actually load the data, whether that be text or image or something else, you can do that. It also has several different APIs for evaluating based on the learner that you have to bring back metrics that you can use to verify the validity of that model. And then finally, it's extensible. One of the first extensions that we're utilizing is being able to pull in a TensorFlow model and use that directly within ML.NET. And we'll see an example of that. We can also right now export to Onyx, which is an open source community framework that allows you to share models back and forth from different languages. So like I said before, this has been used for quite a while at Microsoft. In Bing ads, for predictions, for chart recommendations, for design ideas in PowerPoint, even in Windows 10 for Windows Defender. Several different things. Okay, so we announced point one at build, and since then, we've added clustering, recommendation that we'll take a look at, and TensorFlow, the first steps in TensorFlow support. We have the ability to do more validation through cross-validation to be able to make sure that our models are doing what we think that they should do. We have different transforms for example, scoring that TensorFlow model. When I'm working with something like TensorFlow and my images, I get back a score or a percentage of confidence on what I found in that image. Is it an orange? Is it an apple? What am I looking for in that image? What am I pulling out of it? Is it a digit? Additional learners, so that you can, now we have what's called an ensemble learner. So you can actually combine different learners. So you might want to do a classification, regression, and pull that into the pipeline itself. As I said, there's support for Onyx now, which is that community-based open source model that's supported by Facebook, Microsoft, and several others. We also have improved F# support. Now we, within ML.NET, I believe 0.4, we have support for direct F# record handling in that. And then finally, there is the machine learning samples repo. There's several different samples out there, including a lot of the stuff that I'm going to show you today, so that you can use that to take a look at and get started. So let's jump into the first example. And this one is for GitHub Issue classification. Like I said before, in a repo, like in the .NET Core Effects repo, you get a lot of issues all the time. Wouldn't it be nice? It's almost like an infomercial. Wouldn't it be nice if you could go ahead and label that automatically? How much would you pay for that? Just wait. You know, so it's one tangible example you can use for machine learning. So in this, as I said before, if it's classification, we're looking, is this A or B? But not only that, because we have more than 2 labels. So it's multi-class classification. So which label should this issue be assigned? Is it a language? Is it something within the operating system? Is it something even buffering? There's, as you'll see when we get started, there's probably 30 labels that one of these could be. So let's go ahead and take a look at that. And so here's an example right now. Notice that we have different labels here. Actually, I'm going to go out. I'll just go out to the repo. Let's do that. The neat thing about the .NET repos is they all start with .NET. So let's go ahead. I'm going to turn up the font. Can you see that in the back, sir? You see it okay? Cover your other eye. Let's try that. Okay. So let's take a look at some issues. And so now we have several different issues that's here, and you can see that we have several different areas here. Some for memory, some for security, whatever that might be. So if we have a new issue, we can then try to determine or predict what that label should be. And if it says something like, I don't know, .NET Framework, then the label's probably broken a little bit. Okay, so let's go ahead and jump into that. Code. Sure. No. Leave me alone. Okay. So inside of ML.NET, we have a console application here. And inside of our NuGet package, we've got several different APIs that we can take advantage of. And in this case, we're going to be using several different aspects of that. So the first thing that we do is we have what we would call a pipeline. And really the metaphor for the pipeline is similar to what we might do with debugging, where we want to keep the context and everything together. And in this case, while it's really good to have a linear flow, sometimes we may want to decompose parts of that pipeline and utilize that in different ways. Pull out different trainers and use the products of that in a different part of the workflow. Currently, we can't do that. So one of the things we are going to see today is the changes that are happening in the API as well. But before we get to that, let's talk through the concepts of how we would use this in our in ML.NET. So the first thing we have here is our learning pipeline. Then we actually load the test or our training data in. And we also have a schema here that we can use. And so let's take a look at that. If I scroll down to the bottom here, here is our GitHub issue coming in. And notice that we have the actual issue ID and the label that we're going to utilize, what's the title of the issue, and the description. And notice that we have columns, it's adorned with columns there so that we can determine what position those things are. And we're going to use that then with our prediction to determine what that area should be. Okay? So let's go through that, shall we? So I'm going to go ahead and start this up. Okay, so here in our pipeline, we can see that we have some rows built in. That's pretty small. Let me magnify that real quick. Okay, there we go. So as you can see here, we can see that schema there. There's the ID, the area that we want to use, or the information we want to use to train our model, the title, and then the description. So now that's thinking, okay, John, that's great. We can see that. So now we want to take a look at that, though, and see what happens next when we start to transform that. So the first thing we're going to do is we're going to tell in our pipeline that our area is our label, the thing we want to use to train this model. And so this is what we would call supervised learning. And supervised learning basically, well, it doesn't basically, supervised learning has the pattern that we want to teach or that we want to train the model with inside the data that we're using itself, so that it has an example that it can use to go, okay, I understand. This is a good, and if we're talking in terms of like text analysis or something like that, it would be, this vacuum cleaner is great, and that would have a positive sentiment next to it, so on and so forth. In this case, what area would all of this historical data be attributed to? Okay? So let's go ahead and step into that. Now, let's take a look at this. There we go. So we can see, pull this up a little bit, and there's our label right there that we're going to utilize. So basically what we want to do is take the non-numeric pieces of data and turn them into a numeric equivalent. Because what we're trying to do is figure out, okay, is this close to what I'm trying to predict? And we do that with numbers and magic. Okay, so now let's go through, and you notice we had the title there. Let's take a look at that, and notice that we have now, with our text featurizer, we've changed that title into a representative set of numbers. Once again, so that we can then utilize that to determine the percentages, and that's what the model's actually going to use to train from, and we call that a numeric vector. So where would you go to find out more about machine learning terms? I don't know, John. Where would you go? I'm glad you asked. If you go to docs.microsoft.com, there's an ML.NET guide there, and there's a handy-dandy pocket-sized glossary if you have a phone that will fit in your pocket. So we can go out down here and say, okay, what is a feature? So basically, it's breaking down that text into something that we can measure. It's trying to measure the unmeasurable, okay? We can measure a number, right? We may not be able to measure a title of, the link is broken in this document. How do you measure that? So we take that and we break that down into what we would call a numeric vector. And there's all sorts of fun terms. So if you're having trouble sleeping late at night, you can pull up the glossary with a glass of warm milk and it will help. But seriously though, we've tried to pull in a bunch of different machine learning terms because really the target of this framework is for developers that may not have had much exposure to machine learning. Okay, let's go back to the code. Okay, so now we're going to do the same thing with our description. And now we can see that in place of the description, we have another set. We have another vector there. Okay, so the next thing we're going to do is we're going to add our trainer. Because we're going to classify this as a multi-class classifier. And then we're also going to go through and tie in the predicted label with our converter. We'll see that in just a second. So this is almost as fast as running it normally, I realize. So once we've done all that now, we take the issue that's coming in, and this is our input, this is our output. So we use that to predict. Then we're also going to write out the model asynchronously, and that would allow us to pull it back in to utilize it in, I don't know, whatever we would want, an Azure Web Service, or pulling that into, exporting that to Onyx, using that, then pulling that into like CoreML or something like that for a phone, using that inside of a Raspberry Pi to measure discrepancies or anomalies on a manufacturing floor, something like that. I mean, you have that model, and that's really the expensive part of the machine learning, is training that model. Okay. You want that. There we go. So we're going through, and while that's running, I'm going to walk through some more of the code. But basically, we have some different parameters that we can use that are outside of the model itself that allow us to tune what's going on with the model, and those are called hyperparameters. And so basically that allows us to take that model and tweak it in such a way that we can get more performance out of it or make it more efficient. Hyperparameters, ask for it in your grocer's frozen food section. So basically we're going through and using the classifier to determine and train the model itself. So the next thing we're going to do is write that model out as a zip file. And then notice what we're doing next. We're simulating using this in another application. So we're going to read that in asynchronously and then use some test data. Well, I just used a bunch of training data. So what am I going to use for test data? Wouldn't I just use that same data? I mean, the test would look pretty good, right? If I use the same data, it's going to look phenomenal because I just trained on it. I'm like, oh, yeah, sure, that's whatever I'm trying to do. That classifies perfectly. So what we want to do instead, that can cause, if we would do that, that would cause a problem called overfitting. So basically, overfitting means that when we're creating our model, we're going to get a false sense of correctness because we're using the same data. So it's a good practice on the data set that you're using to train to take about 20% of that, split that out, and use that for testing. So we can evaluate that and see what the accuracy of the model might be. And what that also simulates is the ability to use historical data to train our model and then use new data as it comes in to test and evaluate that, or to actually use it in production, but making sure that we have the accuracy that we need. Okay. So now we're going to use our text loader once again to load in our test. And remember we saw on the framework diagram, we have several different evaluators that we can use. In this case, since we're doing classification, there's a classification evaluator that we can use. And it's going to return some metrics. Come on. Okay, so it came back, had a little bit of an issue with some formatting, but we processed a little over 3,000 rows and evaluated that. And so now we're going to use one of the metrics called micro accuracy, but really it's more apt of a term to say it's a micro average. And I'm not talking about little bitty cars and what the average size of that is. Talking about micro average would be how well each area performed as it went through the training. Okay, like for example, like system I/O in that area, or metadata, or whatever. You know, how are the individual classes themselves? How did they perform? And that gets aggregated up. Okay. So let's go ahead and predict on the issue itself. And so we've got about 73% micro accuracy there, which isn't bad. So now we're going to go ahead and take some sample data and predict on a new GitHub issue. In this case, we've got our title. It assumes the result of get method will be not null. Sounds like a party game, Trivial Pursuit or something like that question. So we'll see what it determines that is. So let's go ahead and predict that. And it says, come on. There we go. It says the area is system.link for that particular issue. Okay. So that's actually being used today on the repo. The model's being used to determine what the labels are. So just to review, we have two different items of data that we're pulling in for input that we're going to take a look at. And those are our features. It's title and description. We're using our label to train the model so that we know, so the model knows what to look for prediction. So once again, we take the features and our label, and we train that, and it outputs our model. Then we use the prediction to go ahead and have our predicted label. So I talked a little bit about this before, and we just saw this in the demo. We load our data, we take our labels and our plain text, and we extract our features and change those things that we really can't measure easily into numeric values that we can measure more easily. We train our model, and the model's the output. We evaluate that, and any data scientist will tell you that right here takes up a lot of time, okay? And that presupposes that you've already gone through and identified the data that you want and the question that you can actually answer, okay? So it's knowing your data and then knowing what you're really trying to answer to get to this point, okay? Because, like I said before, this is a real iterative process to determine whether or not you're really getting back either what you think you should or something totally different. And you keep using the evaluation to make sure that that's right. Because once you get to this point here to model consumption, it becomes way more expensive to pull that back from production. Has anybody experienced that once you put the model in production, it's more expensive to try to pull that back than trying to really tune that down? Kind of like what the architect Frank Lloyd Wright said. He said, I'd much rather use a pencil on the drawing board than a sledgehammer on the construction site. So much less expensive there. Okay, so we talked a little bit about classification. Let's talk a little bit about movies. Who likes movies? Anybody like movies? Okay. Can everybody stand up? Everybody stand up. It's the afternoon, right? I mean, we're talking about statistics and machine learning, right? So everybody, if you can, just kind of do this. Let's stretch a little. Just do a little stretch. I don't know how to do yoga. Otherwise we would, but just stretch up a little bit. Let's kind of get loose, you know. It's the afternoon. Okay, good? There's a little bit of a break, right? Okay, so favorite movies. Favorite movie categories. Sci-fi. Film noir, okay. Action. Anybody else? Horror, okay. Comedy. Right? Anybody like westerns? That's supposed to be John Wayne. Not very good. It's okay. Westerns, comedy, everybody has things that they like, right? So how can you use machine learning to build something that has a degree of confidence that you can recommend to somebody? Wouldn't you like to know the answer to that? Kind of like how to buy real estate with no money down? Stay tuned. Okay, so anybody watch Netflix? Anybody like the preview thing on Netflix? You know, it starts up immediately and it's, you know. Anyway, once again, I'm on pain meds, so I apologize for the, Okay, one approach that we can use is population averages. Although, I think I'm using that word in a way it's not supposed, you know, I do not think that word means what you think it means, right? How many have seen The Princess Bride? If you haven't, you should put it on your bucket list. It's a pretty interesting movie, okay? I mean, it's got an IMDb rating of greater than 8.0, okay? It's got Billy Crystal in it, and all sorts of people. It's great. All right, but you can use population averages to go, 20 million people, 20 million, sorry, pain meds. 20 million people really liked that movie. It was the feel-good movie of the summer, right? That can kind of work if people actually like it. But there's some flaws in that approach. Because what's the biggest flaw in that approach that you can probably see? This is the interactive part of the show. So,
get a movie with 1,000 users but rated as 4 stars, and that will also match. Rated as greater than 8, but that will also be in the same category as this movie.
Right. What if you're not one of the people that thought it was 4 stars, right? What if you don't like this, this movie? Yeah, but I mean, if we're trying to give a recommendation for you, population averages will only take you so far. Okay. Content-based filtering. Do you like Iron Man? Do you like Captain America?
Yes.
Then you'll love Iron Man 2. The second one. Not so much. Yeah, those of you, that's kind of an inside joke. Those of you who have seen, how many of you would say that that would be a valid recommendation? That you'd like Iron Man 2? Would you? Okay. What about if we said, okay, you've seen Iron Man, you've seen Captain America, you've seen the Hulk, you've seen the first Avengers, the second Avengers, all the Captain America movies. We think you would like Notting Hill. There's something broken with that. But anyway, we can use content-based filtering to go, okay, John really likes superhero movies, and so I'll recommend Infinity War. And he'll willingly pay out his money and go see it millions of times and get it on DVD and watch it again. Okay, another approach that we can use is collaborative filtering. Collaborative filtering allows me to get a recommendation based on what other people who have similar likes or dislikes like or dislike. So, these are some of the people on our team. Ankit doesn't like the movie Heat, doesn't like Mission Impossible. The X's mean don't like, okay? Home Alone, Terminator 2, didn't like Casino Royale. Gal, he liked Heat, Mission Impossible, didn't like Home Alone, liked Terminator 2, will he like Casino Royale? John, or Cesar, either one, liked Mission Impossible, liked Heat, and actually this isn't true because I did like Home Alone, but that might be a different John. Terminator 2 and Casino Royale, okay? So basically the premise is that if person A has the same opinion as person B, then A is more likely to have B's opinion on a different issue than a randomly chosen person. So the question, once again, we come down to a question that we want to answer. One question, right? In this case, what's the probability of Gal liking Casino Royale? And so we released what's called factorization machines that allow you to do this type of analysis. So in this, you have to pick a data set, right, to answer your question. We talked about that. In this case, we're using the Movie Lens data set. There are 20 million ratings, 27,000 movies across 138,000 users. Okay. And it provides you with the movie information itself that has movie ID, title, genre, and then user ID, the movie ID, the rating they gave, and a timestamp. Okay, so factorization machines is a binary classification learner. We talked a little bit about binary classification versus multi-class classification. You can say that 3 times fast. So we have to model this as a binary classification problem. And since the scale inside of the movie lens is 1 to 5, we've got to come up with another way to do that. And so in this case, it was decided that if it's greater than 3, it's recommended. If it's less than 3, it's not recommended. Okay? So basically we take that rating and then change it to a binary value that we can measure. So the essence of machine learning is that we're trying to answer a question based on data that we can accurately measure to determine the validity of an answer to that question. Does that make sense? So basically we use numbers to determine yes or no or what something particularly is, okay? In its most basic form. Okay, so let's go over here. This is a little bit better than just, hey, let's walk through the code. But it was good to get the concepts of seeing how we transform different types of data into something that we can measure. And I keep saying that because it is important. Okay. All right. So in this solution, we've got a couple of different projects. One is actually helping us create the model, and the other one is letting us what we would call operationalize that, or use it in production. In this case, we've got an MVC project that's our little movie site recommendation. So let's take a look at that first, and then we'll take a look at the code behind the scenes. That's interesting. That's kind of hard to read. All right. Takes it a moment to load up. So we've got a movie recommender right now. So does anybody remember what the question is that we're trying to answer? Right. Does Gal like Casino Royale? So let's go into Gal, his current profile. And notice here we have some recently watched movies, all-time box office movies, and click on the recommended, and I ran this in debug. I didn't want to do that yet, but let's go ahead, continue, yes, continue, yes. Here we go. Okay, notice here that the recommendations, Face Off is about 55%, Home Alone is about 30%, Casino Royale is 84%, Titanic, 56%, and Gladiator is also in the 80s. Okay, so if we remember correctly from our graph, Cesar is very similarly, he likes the same sort of movies. So let's see what the recommendations are for him. I'll put that back on in a minute. And so here, notice that Casino Royale is 87% there, Gladiator is 85%, and they're very similar. Now, one of the things that happened with this data is when we created this, we kind of cheated a bit, because if you remember, Cesar's already seen Casino Royale. So we uploaded that for training purposes. Okay. So now, let's go ahead and see the magic behind this. So we broke this into two parts. Let's stop this real quick. So once again, we have our build model, and we're loading our text again. And in this case, we're using something new. And this is called a categorical #1 hot vectorizer. So basically what that does is allow me to take non-numeric information that we want to use as categorical and create a vector that we can use then to measure categorically across different parts of the model. So we do that, and we bring in our user ID and our movie ID, because a user likes several different movies, and a movie can be in several different genres. Then we take those and we combine those into a column called features that combines the numeric vectors for those. Then we go ahead and we use our learner, and notice that we're passing in several different parameters to make that more efficient. Pulling in our data just like we did before with our actual data. Our user ID, our movie ID. And this time we're going ahead and identifying the label that we want to use for prediction. And then here's our predicted label that we're going to use as the output. And we simply run that through and get our metrics out, and we can see that. I'm not going to run that part right now because it's 20 million records, and it takes a little while. Okay. So we can massage or wrangle that data, though, because remember, it's a binary classification part, and we want to be able to go ahead and use ones or zeros, but since we're on a 5-part scale, we need to be able to break that out. So basically, we're going through and changing that rating as needed to either 1 or 0. Creating our data set, going ahead and sorting that out, and then here is that part that I talked about where we're splitting the data out, part for train, and then another little part for test, so that we can use that effectively. Okay? And so that's creating the model. And then in our controller, we go through, we bring in the user ID for our profile, we grab that profile, we load the movie recommendation model, which is what we built before in our other application. We go through and we set up our matrix for our ratings, our movie ratings, and our watched movies. And then we go through and we grab the watched movies and make a prediction for that. We return that view. And the one thing that we do is we take the rating that comes back and we make it, we convert that to a value between 0 and 100 using a sigmoid function that we've created. Okay? So we use that then to recommend the movies. Okay. And then finally, we have the image classification that I'll show you real quick. And I have a data sheet that's going to be coming out with a bunch of different links and also the projects, where the projects are themselves. Okay, let's do that real quick. And the slides will be available. So I apologize if this has been a little disjointed, circumstances being what they may. Come on. And this will also be out in the samples directory probably early next week. Come on, come on, come on, come on. Okay. So here, we're using the inception model, and that has been trained on about 1,000 different categories of images that we can use to actually pull in an image and determine what category it's in. Okay? We have a data file that has several different images in it, a shark, a puppy, all sorts of different things. We go through, and this is actually utilizing the new API that allows us to independently instead of linearly go through and load that text up, or that text up via text loader. Notice that we're loading our image path. And then down here, we're creating, after we've read that in, we're estimating that. We're creating an estimator that we're going to use to train and then estimate. We're loading it up as an image, we're resizing it, and then we're extracting the pixels. We're then going through and using some of the data for the TensorFlow model itself, pulling that in, and then using the estimator to score the data. And what we mean by score then is that you're going to get back a number that shows how confident you are that this is a dog or whatever you're looking for, okay? So go through and we read all the lines and then write out that label. So let's go ahead and try this so you can see that. And so this one says that it's a great white shark. Yes, sorry about that. So it is shark.jpg, and I will go back and do that. Oh, size. Yeah, you mean the size. That's it. No. There we go. It's done. Okay. All right. I apologize. But it did come back and say that it was a great white shark. And we're done, he said. So if you have other questions, feel free to, I'll be around. Ask me any questions that you want. Again, I apologize if it was a little disjointed. I'm actually in a tremendous amount of pain, and I'm on pain meds right now. So I hope it was at least a little bit valuable to you, and I appreciate the time that you've spent today. So thanks a lot. And if you have any questions or want to see something in a little more detail, I'll have the machine. And so I'm here for the next couple of days, so whatever you want, okay? Thanks a lot.